now, but most of the people are not back yet. So
See whether
give us
there
2
is-
minutes, please. Oh, you want to sit here? Okay.
Did you take food down?
Hmm?
Did you take food down, or did that begin to sort of pitch to?
Don't take food there anymore because they are.
The coffee.
Oh, I see.
They're waiting crowd students every day to pick up.
Oh, you want to sit here? Okay.
Oh, sorry.
The problem is that there's just too much left over.
Did you take food down?
Even PhD students
Did
gonna
you
be
take
just piling up there.
Oh, come on, really?
Yeah.
You just take it home and store it and whatever.
Most- Quite a bit of it's wrapped, so you can
I-
take
I-
the cookies with you and just say stash them in a cupboard somewhere.
Yeah.
You pay your students too much if you don't take it anymore.
Is this? So
Shall we start or I don't know.
are we on record already?
Yes.
Yeah.
Okay, then let's start. So, hello everyone, I'm Andres. I'm going to be chairing today's discussion session. So I'm just going to copy paste the link where you can technically post topics that you want to discuss. Oh yeah, Ariot already posted, sorry. Okay, so you use that link to check the topics that we can discuss. So for those of you who were not here yesterday, actually we have discussed all of these topics so far, except the first one. So we might as well just start with that.
I think we only got through 8 of them yesterday.
Sorry?
Shane, could you repeat?
I think we only got through the first 8 on the Padlet yesterday.
But there are then only 8, no? Because the last one is
Oh, sorry, there were 16 yesterday.
That number is for all of the 3 discussion sessions, but we're only looking at the stellar binaries, of which
Yeah.
there are 8.
Oh, we can talk about them.
Oh, if I open it up, it says there's 15 of them. So
but only look at the stellar binaries multiples, and then you'll see that except the first one, we went through all of them.
oh, I see. It puts all the Padlets together.
Yes, exactly.
Well,
Okay, but then let's
Okay,
start
I understand. Yeah.
with the topic that Valeria posted. So
If you have the screen, we can share it to Zoom,
sorry, I can share my screen.
Mhm.
Oh yes.
so everybody can. see.
Oh yeah.
This
Okay.
is-
Sorry. Okay, let's do that.
Sorry, guys, we're a bit tired on this side.
You've been doing a lot.
All right. So can you guys see it properly?
Yes.
If
You
you go on those three dots, it will be open post. And it's post.
Oh, great. Okay. All right. Yeah. So can we learn something about the Milky Way's structure or density profile from these data? Maybe you should actually talk about this.
Yeah, so this actually was an example question, but we can like use it as a warm-up. And everybody else are welcome to meanwhile add other topics or just we go without Padlet freestyle.
Yeah.
So basically, I guess what I would like to ask this community is that it looks like if we take the result sources and especially those at frequencies that are green and yellow, so frequencies above like a couple of millihertz, where LISA is the most starts to be the most sensitive. Those double white dwarfs can be used as stellar tracers. So we can actually map the full disk of the Milky Way and this even characterize the structures within it, like the bar. But my question to the audience was maybe I am missing something, right? And this stellar tracer may be biased for some reasons.
Can we? Can we? Maybe that's the question. Maybe I should read the paper. But can we really? Because we don't know if they're old population or young. Because we only get the frequency and the distance. Maybe do we even get a distance?
Yes.
For some of them,
Okay.
yeah.
We get a distance and a frequency, but we don't know.
Yeah, but even if your errors are large, right? If you go through a hierarchical Bayesian machine, it will take your uncertainty, like you will have more weight for binaries with small errors and less weight for binaries.
But for population of binaries, we don't know if this is a young population, white double white dwarf, it's an old population, if this is a halo population, if it's a thick
Yeah,
or
you
thin
don't
disk.
know, but you can talk only about the shape, right? You cannot talk about like young, old.
Exactly. Okay.
So Tyson, your hand was up and then you put it down. Did you want to say something?
I was going to comment on big error bars on distance and having to do some hierarchical analysis, but Valeria is way ahead of me.
Okay.
No, but I mean, it's a good time to, if you still want to comment, I mean, you're free, you're welcome to do that.
My comment is I agree.
Okay.
I have some stuff to show, but Alexei, you can go first too. So yeah.
Yeah, well, just talk to the, I mean, like, so in principle, we might see their old population. For example, if, like Thomas said, if you see white dwarf binaries in the halo, then they're pretty old population. And in principle, if it was possible to follow up some of them and get rid of velocities, we might also correlate white dwarf binaries with some old stellar streams and halo substructures, which would be really interesting because then I would know the ages for them. And well, I mean, probably it's very hard though. And also, yet another thing is that, you know, for example, we could see through dust pretty well. So I mean, in the places like galactic center, especially populations in the very center of the galaxy are really badly constrained. And I mean, there's lots of puzzles in there. And if Lisa says something like unusual happening in the direction of the galactic center, that probably would be very interesting to people who model that. So just these points.
I would be really careful with VM. There we are really limited to a kiloparsec, maybe 2 or 3 in the ELT times. But I mean, and getting radio velocities is impossible because you have to, there we have to deal maybe with photometry, right? If you get LSST color, something like that, maybe that tells you something, at least the temperature. But you really have to. Yeah, I don't think so. Maybe
no. Just but the point is that, you know, when Lisa comes, it's going to be in 15 years from now. So I mean, there's going to be all these ELT things, and I mean, the spectroscopy will be much better. I mean, and you know,
I know. there's the above. I mean, Valeria had her paper where she showed that like 90% of the double white dwarfs will be 30 meg or fainter, something like that, right? And yeah, it was crazy. Some of these 80 meg or whatever. You need a lot of ELT to put together to do something useful.
So the 1 kiloparsec horizon you mentioned, is it for the current instrumentation or for the ELT-like instrumentation?
That's for the current.
Okay, and ELT then therefore will be at least factor of few better.
Valeria did that in her.
Yeah, it's like a few kiloparsec for LSST, so 24.
Mhm.
and
But without outside the galaxy, outside the galactic plane, right? Because you get right
yes,
in.
yeah, and it will be on high latitudes,
Exactly.
at high latitudes. But like I was curious, maybe you guys can think of any biases, like something that came up yesterday, not on this topic, on double white dwarf or white dwarf receiving kicks, not on kicks or something like that. I mean, just as an example.
Yeah.
That's constrained. I mean, white dwarfs at birth do not get kicks. They might only get kicks if you do some supernova with a companion, then they might be kicked. But I mean, there's the observational constraints that they have white dwarfs at birth from AGB stars. They get velocities lower than a few kilometers per second, so like it's not a kick.
Can I just add? Sorry, I'm in the bus, so if the sound is really bad, I hope you can hear me. But I think maybe we need to be a bit careful with saying no kick at all, because I think there are some indications, for example, the work from Al-Badri et al. Based on Gaia, that there could be a kick up to like 1 kilometer per second. I mean, this is still within the area that you said, right? So small kick.
Can we get those from Lisa? Can Lisa constrain it down to 1 kilometer per second or less?
Lisa doesn't constrain velocities, right?
I think the orbital velocities were probably much larger than that at that point. So 1 kilometer doesn't really matter, I expect. But you might see it through weird channels, because this 1 kilometer per second, it matters for the very wide systems. And if you can get LISA sources from triples, they may come from wide sources. So for example, eccentric double white dwarfs may give you a handle on it. But these are quite exotic channels, right?
Can I ask what causes the kick for white dwarfs?
That's a very good question. It's more that we. Sorry, I need to change buses. Can I come back to you in 5 minutes and say that?
Sure.
Reschedule the bus, Sylvia. Come on.
And this goes on YouTube, right?
But if I may fill in for that, I mean, so like we know that white dwarfs are born after AGB stars do thermal pulses, and thermal pulses are, they do like 10 thermal pulses and that's it. So they shed a lot of mass and then you get white dwarfs. I mean, and whether it's very symmetric, we don't really know. We have nebulae which are, kind of a bit asymmetric. So I mean, maybe that asymmetry might generate some small kicks.
But if it is this asymmetry, then it's not relevant for double white dwarfs, because the envelope is removed via mass transfer.
Yeah, exactly. They all come post-com envelope systems.
So I talked to Evan Bauer about that, and so like, I mean, some close white dwarfs might be made from SDP stars or SDO stars, maybe. I mean, so and some of the models, especially latest MESA versions, which resolve the helium burning phase and shell helium burning phase in those subdwarfs. So they indicate that even if you have a thin layer of for example, of hydrogen, or for example, of helium at the end. So anyhow, so those subdwarfs still can do some pulsations. So that's what Evan says. So, yeah.
Okay. Thank you. Anyone else regarding this topic?
I think the only thing I'll add is that, we've thought about this before. Lots of us have. Tyson and I did it a long time ago, and Matt Benequist and I did a long time ago. And what's interesting about this question is that if you just look at the LISA cut, the shape of the galaxy, you just plot where the stars are that we know we've extracted. They're absolutely, the shape of the galaxy is in there. What's the difficult question is, how do we get it out? And so I think, at some point, staring at the data and thinking about not necessarily what will LISA tell us, but is there any way to get more information about the stars that we absolutely know LISA can resolve, at least in terms of the gravitational wave signal, maybe not the distance, then maybe there's a handle on this problem that we haven't thought about. But if you just look at the cut on the LISA catalog, there's biases to the stars that are close to us and to the center of the galaxy, et cetera, et cetera. But the shape of the galaxy is absolutely there. And I think there's maybe thinking to be done there about other data sets you can put on top of that might couple. So Tyson.
Yeah, I'm going to push back a little bit. So at sufficiently high frequency, according to our current best estimate of what the galactic binary population in the galaxy is, the LISA catalog is complete, which is really handy.
Sorry. What does that mean, Tyson? What does that mean?
It means you see every binary.
Oh, nice. Okay.
Now, when you're doing these hierarchical population analyses, you're dominated by the best constrained things. And so those would be the things at high frequency where you have a complete catalog. Yeah. But the lower signal to noise, the less constrained things also contribute. They build up more slowly, but you have gazillions of them. So what I think is the big question here, which is really, really hard to answer without like gigantic computers, is it worth digging into the lower frequency part of the catalog where you encounter all of the different selection effects? Or do you basically get everything you're going to get anyway, just using the brightest sources in the population that the selection effects pretty much go away? I don't know the answer to that. I think it's a really interesting question and probably depends very heavily on the specifics of the, what the galaxy really is.
So Andrea Lohman and I always called this a few good sources versus a bunch of crappy sources.
Yeah, I can apply it.
Oh, go ahead.
So I think that, in my view, probably we will get the shape of the galaxy from resolved high frequency sources, but then the how many are double white dwarfs are there in the galaxy. So for instance, the total number, then we will need to dig out into the low frequency ones. So those who would tell us like how big is the population.
Can I ask? Sylvia.
Sylvia.
Sylvia. Sorry.
I had a question still about the biases. So I was wondering, I think it's really cool to hear that we can observe all of them, but how about constraining their parameters in the sense of, having a good constraint on chirp mass? Would there be biases in those measurements? So if we go one step beyond just knowing that there is a source.
Yes. No, I want to hear Tyson first. Yeah.
Okay, so above a certain frequency, basically where the confusion noise turns off, so let's call that above 4 millihertz, you see everything, and with a long enough observing time, you get F dots on pretty much everything. These are the high frequency binaries, so you're more sensitive to any sort of frequency evolution. Plus, they're all pretty dang high SNR. Where exactly that line is and how many sources live above that line where the catalog is complete is part of the reason that I was advocating during the last hour for more galaxy simulations to play with, because we have a lot of intuition built off of order 1 simulation. But I can guarantee you can draw a line somewhere in the LISA catalog where above it you can ignore any sort of selection effects, including on FDOT. It's just the big open question is where that line is.
What limits that line?
Sorry, guys.
Confusion noise.
Okay.
Can I ask a question, which is, and I don't want to be negative and don't want to be the devil advocate here, but what do we learn about the galaxy? What at least what Gaia hasn't told us in 10 years from now? I mean, because the shape of the galaxy we know, like really the scale height, everything. I mean, the only thing, maybe the scale height of the double white dwarfs, but then we have to know which ones are young, which ones are old. I don't know. This is more out of curiosity. What else do we learn then there's probably something, because Gaia doesn't see the double white dwarfs. Gaia sees all the main sequence stars. But the shape of the galaxy is known. Right.
May I first reply to
Yeah.
Silvia?
Go ahead.
So to reply to the, for instance, constraint on the Chirp mass distribution, we actually checked that with the Nikos. And again, through the hierarchical Bayesian machinery. And what we found that we can recover back, if we use our SIBA simulation, we can recover back the Chirp mass distribution from the lowest up to around 0.7 solar masses. So we don't have, we don't recover back the highest Chirp masses. And that because those are sitting at lower frequencies, so where LISA is not sensitive, so below the famous 4 or 3 or whatever millihertz. That is for Thomas less than 20 minutes.
Thank you.
Or more than 20
Thank
minutes.
you.
So those more massive ones are at least in our simulation, are at larger separation, so their errors are larger, and we just cannot recover back the what we input. But for the lower Chirp mass part of the distribution, we can very well recover it back.
Can I rephrase that and then you tell me if I understood it correctly? So what I just learned from Tyson is that the cutoff is based on the confusion noise, but that the models are saying that there's a dependency on the mass as to at which frequency you are. And so even though LISA might not have a bias, in the population there might be a bias because inherently there's a dependency on mass and frequency. Is that the way I could look at it?
I think
Yeah,
so.
I agree with that. So Lisa is seeing like an extreme tail of the population, but at least you get a very clear view of what is happening in that extreme tail of the population.
And it tells us that we need to understand that part of the models, right? Where those dependencies come from.
It's probably the hardest part, right? With tidal heating and everything. It's the final
I think
stage.
but might this not be what like systems that are wider, so that tidal heating doesn't really matter yet? Isn't that only just before contact?
Oh, yeah, that's right. That's true. Yeah, that's okay.
Yeah, I think you're correct, right? Because at different frequencies, we have binaries of different mass and kind.
Yeah.
And the older one with lower masses are, well, at least in the model we consider, they are sitting at the higher frequencies, while the higher mass binaries are sitting at low frequencies. And this is why we don't recover them back.
Alexei, your hand is up.
Yeah, this is to Thomas' question, like what can we learn beyond Gaia? So, I mean, one thing is that Gaia is observing like 2 billion stars out of like, I don't know, at least 10 billion stars, even more. So, I mean, and Gaia doesn't see really well beyond like, I don't know, especially in the bulge direction, and doesn't see the other side of the galaxy. And I mean, in fact, people try to push for Gaia near infrared to actually be able to see those stars. And that's a big mission, which probably also gonna fly in mid-2030s. And I mean, like, and LISA can do that. So I mean, LISA can see through the bulge and on the other side of the galaxy. So that's really valuable, actually. And on top of that, I mean, for example, before Gaia, people thought that the galaxy was nicely arranged, pretty stable disk. But I mean, with Gaia data, it was clear that actually the outer parts of the Milky Way, in fact, are influenced by, for example, for Large Magellanic Cloud and by other dwarf galaxies which are flying around. And so, in fact, it's like there's a distortion in the galactic disk in the outer parts. And I think there's no way to tell it what happens on the other side in terms of those distortions without having something like LISA, which will see through the disk. So that's probably quite valuable for galactic people.
I wonder, well, that's probably, I wonder if we have enough LISA objects to see the same structure, like nicely resolved LISA objects with a good distance, like a good distance, a good side position to see that structure. Right, for that you need a good distance. I'm hopeful.
I think that you definitely see the profile
Yeah, the profile. Yeah.
and structure.
Okay. Anything else related to this? No? Okay.
There's no question.
You have anyone has a new topic?
I want to ask a question to Sylvia, actually,
Go ahead.
because that came up more and more, especially with Alexei's discussion on triples. And I don't know if anybody ever thought about that, but how many systems and how many Lisa double wide dwarfs are we expected to have that as a third companion, which is a main sequence companion, which outshines the double wide dwarf in the center. So basically, we see the gravitational wave signal from the double wide dwarf, but when we do EM observations, we don't see anything because of the third companion. How many did anybody ever estimate how many are we going to miss in EM because of that? Because they're hiding behind them.
Yeah, so this is things that we're working on at the moment. Camilla already told us the other day a bit about the work we were doing on planetary companions, but the same we need to do for the stellar companions. So it's unfortunately not a question that I have an answer to now, but stay tuned.
What do you think about it? That's important. That's good. Thank you. That's great.
Yeah. I mean, the big question here is how many, we know that triples are common on the main sequence, right? So for solar type stars, 1 in 4 binaries has a third companion. But the question is, how often do systems keep that third companion throughout the evolution, especially during the common envelope phase? If you're not able to, if the system is not able to eject the tertiary star because of this impulsive mass loss. I think that's for me the main worry.
Okay.
All right. So there are no new topics posted. So with new questions right now.
I could ask another one to Tyson.
I think no one else has a question in the moment. So
if nobody else has a question, I have tons. I mean, these few meetings are always this inspiration stuff. Anyway, sorry, Tyson. I really wanted to go back, maybe brief, because you are here now. That's great. So I want to maybe quickly go back to what you said yesterday or Wednesday. I don't know. I think Wednesday, which I had not thought about and really blew my mind. That you basically said that things like HM Cancri, which is on top of other sources, you have to observe for very long until you actually see it because of. Can you explain it a bit more why this is the case? And like, I really would like to understand it a bit better. Right, things even HM Cancri, which is like 100 SNR within, I don't know, a few weeks or whatever. You need to observe longer to see it.
Okay, so what I was saying, it's not that you need to observe longer in order for it to get above a detectable threshold. It's that is, according to the few galaxy simulations we have to play with, that is a sufficiently popular part of the Lisa frequency band that you can have other SNR 20, 50, 100 sources sitting on top of it in frequency. And in order to separate things that are sitting on top of each other in frequency, you need long enough integration times to get sky location and polarization. So it's not, you'll do your search for HM Cancri on the first week of data and you will find something. But what you won't know is if that something is being contaminated by other sources until you have a long enough integration time.
So knowing the sky location from EM is not sufficient at this point.
It's not sufficient at this point. So if we get like really, really deep into the weeds here, that lowers the detection threshold because you're removing degrees of freedom from the model.
Yeah.
And we don't know how many binaries there are. So the challenge of doing the galactic binary search is it's a big model selection problem to decide how many parameters there are in the model in the first place. And if you have a tightly constrained model, it's going to be more than happy to soak up as much signal as it can until it starts to disagree with the data. And the place it will start to disagree with the data is when those Doppler modulations don't match the input sky location. But you know, with short integration times, these galactic binaries just look like spikes in the data. You don't get enough phase information.
I see. Yeah.
So in a model selection sense, if there are two binaries sitting on top of each other at roughly the same frequency, and one of them you know a lot about, and the other one you're completely ignorant to, then the one you know a lot about is going to fit as much of the data as it possibly can. So it can start soaking up signal from other sources. That will go away, right? But there's just this, the first couple of months of the galactic binary analysis, there's like this really like steep burn-in time before you reach a stable solution, because the number of binaries is unknown.
Yeah. Oh wow. Yeah, that's interesting. I definitely learned something.
But I mean, in some sense, contamination by other sources is just, I mean, it's in principle a form of bias. It's always going to be there, because even at the best we can do, right, it's just the best fit to the data, right? And if we had another 50 years of observations from Lisa, it would change what we think the solution looks like.
In principle, that's true. In practice, these degeneracies get broken well before you get to the 50-year mark.
Okay, yeah.
It's interesting. So you're basically saying we have to find a verification system in the frequency range where there's no other source.
Right, but that's impossible, right? So, right, this is a transient phenomena, right? But I'm just raising the red flag that if people say the way we're going to decide we trust the data is that we've observed a handful of the currently known sources, my argument is that's not the best way to do it, because there are better sources in a cleaner part of the frequency band where you don't have these contamination issues.
Yeah, okay.
So maybe the companion question to that then, Tyson, is there are going to be better sources in the frequency band. So how quickly will Lisa provide enough information that the observers can go find it quickly and start EM observing, right?
Yeah.
Yep. So when you have short integration times, all of your sky location information is coming from the beam pattern function, which are gigantic blobs on the sky.
Right.
So within a couple of weeks, when you're doing your initial verification and validation of the data, we can tell you with great confidence that it's probably somewhere in the galaxy, and that's about it. Right.
Oh.
But you let that thing move for a couple of months, and those big blobs in the sky are going to start to collapse pretty quickly. You get like a quarter of the way through the orbit. Now you've gotten, some first derivatives on the Doppler, and that's what you need to localize it. But these high frequency, high SNR binaries are large chirp mass, which means small stars, which means particularly faint, and could be anywhere in the galaxy. And so they're probably not your best bet for the first, sources in the Lisa catalog that you then find in an EM survey, unless we get kind of on the lucky side. But to really understand this, we need lots more galaxy simulations to run through our Lisa analysis codes to find out.
Yeah, that's good to know. I mean, these are also kind of the high gain kind of objects. So it's a good way to get telescope.
Yeah, you only need one, and then you've got plenty to do, right?
Exactly.
So if I come at that, backwards, back this same question, Tyson. So let's imagine, Kevin and his empire of short period binary searches turns up a binary way out there in the clean end of the spectrum. Then those will be very rapidly constrained by Lisa.
Yeah.
Irrespective of how long we observe.
Yes, with great confidence. You get up to 8 or so millihertz and beyond in the gravitational wave frequency.
Interesting. Yeah.
you're a tuning fork in the sky.
Right. Okay. Okay.
It's interesting. That's really interesting.
Okay. Any new questions or topics?
No, sure.
I mean, if you have questions, then go ahead, because I don't think anyone.
Do we have questions like not on white dwarfs?
Wait, yeah, people care about not white. Okay. Do people care about not about white dwarfs? Who cares not about that?
So how about selection effects for eccentric sources? Thinking, for example, not only triples, but also neutron star binaries. There's some work that I'm just trying to remember the references, but from the Australian group and but yeah, exactly. They showed that the eccentricity can actually help you pinpoint the formation channel as well as the supernova kick magnitude. So do we have selection effects against certain eccentricities or dependencies on the frequency or difficulties with templates or? That was my question. Hopefully someone has an answer.
We're all thinking.
Someone called Dyson.
Sorry, Tassos, could you repeat that?
Called Dyson, maybe you have a question?
Okay, I'll wax poetic on eccentricity. So the analysis tools that we've built so far blissfully ignore the fact that there's eccentricity or third bodies or etc. And I have thought about what you would do if you think there might be a handful of unusual binaries in the catalog when you have 10,000 things to sift through that are all basically boring circular orbits. And so I see this as a ripe area for like a LISA guest investigator program. So we'll publish our catalogs. Our catalogs will assume everything is circular. And then the question is, can you then sift through the catalog and identify interesting candidates to do targeted follow-up analysis or a targeted reanalysis of those handful of interesting candidates, which you think might have a chance of showing you something beyond the usual circular orbits, be it eccentricity or third bodies or tides or whatever. And you're obviously going to want to start with the largest signal to noise ratio, because then you have the most information to play with. And I can imagine the strategy here would be, after lots of LISA integration time, so after several years where you have enough, you can divide the data in half, say, and you have enough signal to noise ratio on either side of that dividing line, that you can do consistency checks. Does what I think the signal is during the first 2 years of LISA agree with what I think the signal is to the second 2 years of LISA up to the statistical uncertainty? And what I don't have intuition for is how much eccentricity, how many tidal effects, how big and short period of a third body you would need that you can identify that the signal is starting to disagree with itself at that level, and then that is your target for going in with more complicated astrophysical models. It's a really, really fun game to think about playing, but we're a long way from playing that game.
Thanks, that was really really helpful.
I can add a thing about triples. So I mean, the thing is that
Alex, I can just follow up a little bit on Tyson's answer. So, seeing the same question from the same answer from the opposite side, would you identify correctly that there is a binary somewhere if it was very eccentric and you were trying to model it with a monochromatic waveform, with a circular waveform, or you may split it into two, or like some kind of
splitting.
Yeah, that's totally a signal to noise ratio dependent question, right? So if you have enough signal to noise ratio in the additional harmonics that you pick up, and you're doing a circular search, you might think you have multiple binaries. And so then that's another way you could filter the catalog to look for candidates. You could just look for some like integer multiples of frequency, and if sources seem to line up and exhibit the right relative phase and polarization content, then that's another one to go chasing after. So that's another handle you might have to search through the catalog that way. I just don't have a lot of intuition for how insane of, eccentricity and signal to noise ratio you would need before you start picking up harmonics in a blind search that way. It's a really good question.
And just to close this topic, perhaps if there is no other, is this is this your vision of how the search will be done, or is it really a working assumption of the LDPG that there is not going to be in the core data analysis eccentric searches? The reason I'm saying this is because I'm a little bit surprised. I understand what you're saying, but coming a little bit from the higher mass, I'm a little bit surprised about it, because whenever we're talking about LISA, we're saying LISA is important because it will give us eccentricity. LISA is important because it will give us eccentricity. And it sounds like this is more of an afterthought for the LISA people.
Okay, so this is, so these opinions are entirely my own. The reason I expect that this is the way that, the reason I have these opinions is because this search is hard enough as is to add, we've got 10,000 binaries to deal with. Each one is characterized by 8 numbers. It's kind of a real headache to add a 9th number that's always 0. And so as far as just like an efficiency point of view is concerned, I think it makes more sense to just go in with the model that is like 99.9% right, and then do follow-up. Now, after like a year or two, if we find a source in our catalog that's acting funny, and then we do some targeted analysis and say, oh, it's tides, oh, it's a third body, oh, it's eccentricity. In future iterations of the global fit, we have to account for that particular source. But trying to search for all of those effects blindly, you just end up with a bunch of parameters that are filling up their priors. It grinds everything down, and you're not really gaining much information.
Okay,
now
so if I translate that to the Gaia approach, it's like Gaia in the first 2 data releases, they only talked about single stars.
Exactly.
And whatever didn't look like a single star, they get it out and they release it now.
Right, but then we have the mechanism to then fold in more complicated models as we continue to integrate, get more data. So we don't have to like repeat this hunting expedition every single time there's a new catalog. But I think for identifying sources initially that require this special treatment, I feel like that's a post-processing thing instead of going guns a-blazing into the full galaxy with like a 12 parameter model when there's only 6 or 7 numbers you actually constrain.
Understood. Thank you.
Alexei had a new question.
Well, actually, just to conclude this discussion, and then before asking questions, I mean, so would it be fair to say then that overall the effect will be of the pipeline that will be biased towards circular systems? Is that fair to say? Of all the population of all the real true population, which will have eccentricity distribution from 0 to, I don't know, 0.1 or whatever, that will have a observational bias towards circular systems, because some of them will not be reanalyzed and something like that, or some of them will be too big to look at. Is that a fair statement?
As currently envisioned, especially during the early days when we're only searching for circular things, then yes, absolutely. Even something that is non-circular, until it has enough signal to noise, will be fit by a circular template and will pick up some biases in phase parameters. So, we got a long way to go. Maybe it turns out that the biases will be too extreme if we do just, ignore eccentricity across the board. And I might have to be disabused of this notion that we can do our first couple of rounds just with circular templates and be happy with it. So, if the population modeling, et cetera, shows that you're gonna really walk away with the wrong conclusions if you don't generically include eccentricity, okay, then we'll generically include eccentricity and work a little bit harder on the search. But any corners we can cut, we're definitely going to want to cut for the global fit, at least at first.
Interesting.
That makes sense. And if I may ask the question, just related maybe. So the question is like, if there's a binary and if a binary does funny thing, for example, once in a while, so will we be able to pick it up? For example, I was thinking that some binaries will have triple companions, and it's going to be a pretty similar situation to what we see in binary pulsars, because binary pulsars are also very short period binaries, and they also sometimes have triple companions. And from time to time, binary pulsars show Shapiro delay, which is a really good thing, because if a triple companion passes in front of the line of sight, it can bend the light, and then you could calculate actually the properties of the companion, the binary, everything is really, really beautiful. So I mean, you could measure a lot of parameters. If in a LISA case, so we have a binary and the triple companion passes in line of sight, probably there will be also a Shapiro delay in some sort of like orbits of the binary. And so the question is, will it be possible to extract that from the pipeline? Maybe the question to Tyson.
I'll admit I haven't thought about that one. I've generally not thought too much about things like that, because all of the gravitational wave emission part happens in the far zone. So I'm not sure that the gravitational wave signal gets Shapiro delayed by a third object, unless that third object is like really far away, at which point we're talking about an awful lot of serendipity that it passes in front, and that would be like a one-time thing. It would just affect a couple of cycles. I think it would be really hard to dig that out.
And
I
really
made
far
that all
away.
up on very short notice, by the way. So
yeah, and really far away. So they mean like many AUs, or really far away would be already when you talk about 100 times binary orbit or something like that. So I mean, what does it mean really far away?
I think someone who knows more GR than me is going to have to answer that.
Maybe we can refer to the work of Robson and companions. Would that be what you're looking for? Also, a PhD student from Smadarnaos, I forgot the name, but they also looked at how you would detect the third companion in gravitational wave emission.
But those were looking at second derivatives of the phase evolution. So if the orbital period of the third object is shorter than the mission lifetime, then you'll see this funny behavior in the phase evolution as you get that extra Doppler from the binary, wobbling with respect to your line of sight. I don't think those papers got into like Shapiro time delay type things.
So those effects, is that if I put it in Tassos's words, would that also be a DR3 thing rather than a DR1?
Yeah, because you need these long integration times. First, you need a long integration time to get F dot in the first place, and then an even longer integration time to get F double dot, and then a long enough integration time that you can say, wait, F double dot's doing something funny. It's like changing sign on me.
Yep.
But Michael Katz just put a paper on the archive about this, and it's not hopeless. So they had some model for how often triple systems appear and did some some estimates of detectability, and it was like not zero, that you would definitely find triples in the catalog. They're just not going to jump out at you right away.
Khan, question.
Yeah, Thomas?
Yeah, sorry, I'll change the discussion a little bit. I wanted to make a point regarding finding EM counterparts of LISA sources, which is that very often when we're calculating the LISA, predicting the LISA background, we focus on the double white dwarfs as the most numerous population. But when it comes to finding EM counterparts, I think we've really got to get to grips with the interacting mass transferring ones, because they are substantially brighter in some cases. So ES set is got a magnitude of around 5.5 absolute magnitude, which is 50 times brighter than a typical, even quite bright double white dwarf. And so there's a huge volume factor in favor of finding mass transferring systems, even though there are many fewer of them. So my guess is that the isolated very short period systems that Tyson was talking about, that you might be able to pick up in the gravitational waves quite early on. If we're going to find any EM counterparts of those, they're quite likely to be mass transferring interacting systems.
Yeah.
They're not easy because it's difficult to predict the mass transfer rates, and it's quite dependent on whether they've got disks or not, which obviously depends on the periods and stuff.
So sorry, you just said they're not easy. They're not easy to predict. They're not easy to isolate in a search.
Not easy to predict.
Right. Okay.
The mass transfer rates are probably not going to be that easy to predict.
But observationally, if you had one, you'd know you have one, right?
Well, yeah, you better pick up very likely better pick up the period quite easily. It might be difficult to characterize much more than that. Depends on the exact system, but certainly you could sort of find a system and show that it's the counterpart of a precisely determined gravitational wave signal, I think, quite quickly.
Mm-hmm.
Yeah, they will have probably very weird chirps, right, going in the wrong direction.
Yeah. Inverse chirps, right? Yeah.
Not necessarily. I mean, like HM Cancri is still going inwards, but
Yeah, although I mean, even if they're still going inward, the rate of the chirp is not going to be the GR prediction, right? So there will be weird gravitational wave fits to it in the LISA data if you don't have some measure of the accretion rate from some other method, right?
No, because wouldn't you just interpret that as being at a different distance? I mean, you might not know what the distance is anyway. So
yeah.
Different distance / chirp mass,
distance and chirp mass.
So I don't think it's necessarily obvious. You won't be able to measure. Typically, you probably won't be able to measure the masses from EM observations well enough to say what the chirp mass should be, and so it may be a bit uncertain.
So I think as a follow-up strategy, you follow up all of them and just be prepared that a good number that you might find will be of the interacting variety, just because there's a selection effect there. But it's not like trying to use that to make decisions about which LISA sources you follow up. We have plenty of time. We should follow them all up.
Oh, absolutely. I don't think you'll have any other way of selecting them anyway for follow-up. So just follow all the interesting ones up, all the short period brightest.
So the follow-up, right? I mean, will there be sources for which it's important that we have follow-up coincident with the LISA data, as opposed to follow-up a decade after LISA's done?
The immediate merger. The immediate merger is like one.
Well, sure. Okay, yeah. anything we want to test GR with, I suppose,
I
right?
mean,
But
if you found something where the the frequency derivative was incredibly high or oddly behaved, but I guess that's unlikely. But otherwise, you can backtrack. It might just depend on whether the optical signal is there or not. You might be struggling, but otherwise, I mean,
in as much as ESA's talking about how they interface data with the rest of the world, they talk about alerts and everything, and they're mostly thinking about alerts for massive black hole follow-ups and stuff. But there will be certainly occasion when the LISA catalog comes out that all of us who work on stellar binaries will be like, man, that's a really interesting source, and we'll want to prioritize observations on them. So I was just wondering if there were any that we'd be so immediately obsessed with that we'd need the observations at the same time the LISA catalog was constantly improving. And
well, I think it does depend a bit. That's an interesting point as to how well you'll be able to extrapolate the phase from the LISA observations. If you had some sort of finite set of LISA observations, how as you go forward in future, how accurate is the phase? Because you really do want to be able to observe them optically at a time when the LISA phase is still precise, I think.
Right,
so
exactly.
It's obviously a signal to noise dependent and frequency dependent, and also length of observation dependent quantity. But gradually to go, you wouldn't be able to predict an accurate phase a million years in the future, I'm sure. So there must be some point at which it loses coherence.
Which will almost certainly depend on the kind of uncertain astrophysics that we don't know at the time we make the observations, right? So
yeah, and it's obviously there's a point about the blended sources and merged sources that could probably make quite a difference to that sort of aspect.
Yeah.
Well, luckily, phase is the thing that gravitational wave detectors actually measure, and then we just do a bunch of hijinks to get amplitude, and we use phase coherent templates. So I would say the coherence length is at least as long as we have LISA, and probably a factor of a few more than that before things go off the rails.
Yeah, I mean, doesn't it? It must depend on the signal to noise slightly, mustn't it, or not? Or I mean, if you're only just detecting it.
It does, but just the detection in the first place gets you like a DC level on the phase, which is probably pretty good. I don't have a number off the top of my head, but I bet it's good enough. And then that just continues to improve with square root of SNR as you ramp up the amplitude of the signal. So I bet there's plenty of phase accuracy here to go around, would be my guess.
It'd be nice to know, actually. I'm not sure I've seen predictions. 10 years down the line after LISA, how good are the phases? Compared to what they are at LISA time, it'd be interesting.
Yeah, Lindsay and I are working on some stuff right now. It'd be really valuable to know that if we knew a number.
Yeah, we generally consider that like the nuisancest of nuisance parameters, but yeah, if it's actually useful, then that's something worth looking at. We usually just marginalize over it.
No, it's extremely useful. I mean, for example, you take HM Cancun, we don't know what the absolute phase of that system is. And that's a very valuable astrophysical parameter to know for models of that system.
Because if we knew the absolute phase from gravitational waves, we know the orientation of the binary to the line of sight as a function of time. That's really invaluable.
Yeah, for that one, it's really, really useful.
Yeah.
Great. Someone write that down.
Yes. No, Lindsay and I need to know this now.
Please.
Just a referenceable number would be great, Tyson, if it's in the literature somewhere.
I think it would be faster to calculate it than look it up. It's not that hard.
Can we? So can we just do that with information matrix estimates, or?
Shane, the information matrix is dead.
I know, that's why you keep saying that. So that's the easiest way I know how to calculate things.
No, but a single source, especially one where you know where it is, you can get MCMC results in a couple hours.
Okay.
Alexa, you have a question?
just continue Thomas's thoughts, sort of a bit of brainstorming. So I mean, when there was a LIGO double neutron star explosion, for example, the first detection of binary black hole, there was so this thinking discussed in the literature that gravitational waves propagate with the speed of light, and that's it. So I mean, that's but then the electromagnetic signal can be somewhat delayed by the presence of interstellar medium and some optical density not equal to unity. So I mean, imagining that LIGO is really precise at phases, and supposing that we have electromagnetic observations which can also give phase really well, for example, eclipsing binaries, can we learn something about the interstellar medium which slows down the electromagnetic signal in the galaxy? That would be probably quite novel, especially if it's on the other side of the galaxy. And likewise, also maybe, I mean, can the precision ever be that close or close enough to make such constraints?
So Katie Brebeck and one of her undergraduates and I have been looking at this for pulsars in LISA binaries. Mm-hmm. So there you can match, you can basically take the LISA measurement of the distance, and if you use the dispersion measure of the pulsar as an input rather than as a measure of the distance, you can invert it for the electron density along the line of sight to the pulsar. Mm-hmm. So there aren't going to be that many of them, but it's one of the only ways that exists to calibrate the models that are currently used for the electron density in the galaxy, which are these old models from Jim Cordes and the radio astronomy folks. So that's the one case of this where we've thought about this, and but I've never thought about it for any other EM. I don't know what other sorts of things there might be. Extinction or something for dust. I don't know. Yeah.
Lindsay, I saw you had a question. Did you change your mind, or?
It's a little off topic now, so I didn't want to interrupt the flow of conversation.
Go ahead, Lindsay. You're good.
Okay, well, it's a little related to
chaotic because we all just do that. So just go ahead. You'll be fine.
I mean, it's great. It's great to see everybody's mind firing with ideas. But I was wondering, kind of related back to what we were just talking about, if anybody has looked at the effects that inclination angle has, particularly because I know that when you have like a stationary signal, or I guess a signal that doesn't really have much of an F dot, I don't know that it really affects the signal much, but I know that we are relying a lot on the multi-messenger side with eclipsing binaries. And in that way, inclination angle really does matter. But one of the things that Shane and I were thinking about, and I think it was, Shane definitely correct me, but I think we kind of put it on the back burner, but I'm still curious to hear people's thoughts about how inclination angle would affect measurements purely gravitationally, and how EM measurements can still affect that even if it's not a perfectly eclipsing binary source.
Oh, right. Yeah.
Yeah. I don't know if that's a good framing of the question, but it just kind of, I think generally the effect of inclination angle, and I feel like every time I ask this question, it immediately becomes, well, you would just have an eclipsing source that's, favorable electromagnetically. But I haven't been able to find explorations of things that are not that case.
Yeah.
For the non-eclipsing sources, especially for the accreting white dwarfs, we rely on the gravitational waves. I mean, the AMCVNs, most of them, we have no idea. We know it's not 90 because they're not eclipsing, and we know it's not 0 because we see the accretion disk double line. But I mean, if it's 40, 50, 60.
So the place where my understanding breaks down there, Thomas, and I think Lindsay, this is what I remember us talking about. So you could correct me if I'm wrong. But the place that breaks down there is I don't think I understand then how signatures like the ellipsoidal variations matter in those systems or not, right?
You don't see them in AMCVNs. That's a different story. And then even if we see them, there's this tendency between, and Tom knows this much better than I do, but I think there's this tendency between mass ratio, inclination, all these different things. But for the AMCVNs, we don't see an ellipsoidal manipulation. The donor star is hiding, so we have no idea.
Yeah, with the exception of that one that Kevin showed, that 13.7 minute one, which actually dominated.
I don't consider an AMCVN. That's a pre-AMCVN.
Wow.
To me, I mean, otherwise, the 39-minute STB, accreting STB is also an AMCVM. Right.
But
So
you're basically right. We don't know the inclinations. I mean, if they're not eclipsing, you're pretty unconstrained. There's always a bit of a degeneracy between what extra sources of light there are and the inclination versus the ellipsoidal modulation. And so
Extra sources meaning like the disk, the impact point.
Yeah. And if they add light in, then they obviously dilute the ellipsoidal, and that makes it look as though it's lower inclination, and it's very then difficult to estimate how significant it is, and therefore get a true estimation of the ellipsoidal. So plus or minus 10 degrees would be quite good, I would say. Which is not very good.
So Tom, are you saying that from the EM point of view or the gravitational wave point of view?
From the EM point of view. So
yeah, because that's what's I think I'm a little bit late to this conversation, just like in my stage of having read any of the literature, but it's very interesting to me that it seems like both parties, gravitational wave and EM, can offer like little bits of information, and it would be interesting to see what we can do when we put them together.
Yes, you should. I encourage you to join the pre-EM LISA observation group stuff. One of the projects, I think project 1 is exactly planning to look into that, like where EM can help and where gravitational waves can help. Right. I mean, inclination is one of those things where, especially for the AMCVMs, I hope gravitational waves can help.
It's sort of interesting because it varies system to system. I was saying HM Cancri has no phase information, whereas Kevin's Eclipser is fantastic phase information. So, so then that opens other thing, as Alexia was saying, measuring the difference in speed between light and gravity waves, or whatever, it's gravitational waves. But it's going to vary, I think, from system to system.
Yeah, although there must certainly be cases where gravitational waves can't say anything, EM can't say anything, but if you put the two of them together, then we could, right?
I hope so.
Yeah, right.
It's a bit difficult if you can't say anything from anything.
Yeah, right.
You may be right.
Awesome. Thank you guys, and thank you, Valeria, for the link that you put in the chat.
Maybe I should look at the chats.
So that's the earlier study from Sveta Shah.
Oh, that's Sveta's paper, right? Okay, yeah.
On information matrices, but of course, maybe there is a Bayesian reference.
We can do this better.
Only Tyson thinks information matrices are dead. So
I was about to say,
astronomers still use them.
It is almost like 10 years old papers. So yeah.
You're just making more work for yourselves. You're just going to have to do it again.
Document your
Rip off
tools.
the Band-Aid.
We'll switch.
Awesome. Thank you guys. Thank you for answering my question.
Alexa?
So following on brainstorms and such. So I mean, imagine that's for detection really. So imagine as a binary plane is processing for some reason. So I mean, we see some things like that in systems with planets and systems with in X-ray binaries, and that happens when you have triple companion, and you could actually make systems which are arranging the spins and they're processing. So I mean, would it be possible to extract such systems from the pipeline from LISA? Will it be possible to disentangle from observations? Varying inclination.
So the angular momentum of the system processing as opposed to one of the components?
Yes, indeed. So I mean, it might occur when the spin of one of the components of the system might not be aligned with the orbit, and therefore there could be spin orbital interactions as well.
Right. Yeah. Can a white dwarf spin be strong enough to do that, or are we talking about like neutron star or black hole?
It could happen if you form a double white dwarf system from a triple, for example. So I mean, closed white dwarf system.
Okay. Right. Yeah. Interesting. I've never thought about that.
I think that studies that looked at stellar mass black hole with them may have calculated this, but I don't remember.
But observationally, from in terms of pipelines, I mean, would it be possible? I mean, so when we monitor and we determine the period, for example, we assume that everything is circular. But will it be possible to, in the early data releases, point out that the inclination is varying, say over 100 periods or something like that?
No.
Mhm.
No, so the inclination information is coming from the relative amplitudes and the different polarizations.
Right.
And to well sample the different polarizations, you need LISA to move because you're changing the orientation of the detector response relative to the source. So this is another one of these long integration games. So you could do, a couple of years, constrain your inclination, do a couple more years, independently constrain the inclination and see if they line up with each other. For the ultra compact binaries, mission lifetime is really, really important.
I have a very off-topic question following up on something from half an hour ago. But this is about the difficulty actually to find the verification binaries, because we always say after a few minutes of Lisa switched on, we should be able to see this source, blah, 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 and we can test Lisa.
That's exactly what we say, Sylvia.
Right?
Yeah, exactly.
Is that what I say?
So actually, how long will we have to wait in order to do these tests that we want to use the verification binaries for to test Lisa?
So my knee-jerk reaction to questions about how long when you want to do something interesting with ultra compact binaries is 1 year, because then you get your full suite of the Doppler modulations, all the antenna patterns changing for the polarization. So after a year, if you know exactly where it is on the sky, you would know exactly what orbital period is, you're probably pretty safe. But until that time, look, if you go searching the LISA data for a verification binary, your pipeline will say, I found a verification binary right where you told me to look, because you have such strong priors on the search. But then the question is that information contaminated by other sources? And once you get a year's worth of data, the probability of there being contamination starts to get pretty slim, because now you need them to be at the same frequency with similar orientations at similar places on the sky, and the odds start to stack against you.
Yeah.
Okay, but that's a statement about measuring parameters or something, right? I mean, to Sylvia's point, a week after Lisa's on, isn't there going to be a spike in the Fourier spectrum at the frequency of HM Cancri?
Yep. And
okay,
you don't know how much stuff is adding to that spike.
Sure, but we'll know it's HM Cancri,
spectrum,
right?
You know it's HM Cancri and friends.
Plus stuff. Okay, right. Okay.
Plus stuff, right? But if you move to the right of the spectrum, the chances of there being contamination diminish very, very quickly. So if you want to do calibration, if you want to do self-calibration using gravitational wave sources, you might as well focus on the place where you have a clean look at the gravitational wave sources.
Yeah, sure. Absolutely.
Is my contention.
Yeah, but there's not going to be any doubt that we see HM Cancri, because there's going to be a line there.
Correct.
Right. Okay. Okay. Fair enough.
The doubt is who's hiding underneath that forest.
Exactly. Yeah. Right. Okay. Okay. Yeah.
So long as Lisa works.
Yeah. Right. Lisa's going to work.
These are all conditional probabilities on Lisa working. Those are table stakes here.
I thought that was why they were called Lisa verification binaries. They were verifying that Lisa worked.
Yeah, but that language comes from before we even knew we could detect gravitational waves with anything, right? So
yeah,
I think that bias is decaying away.
No, yeah, space missions, yeah.
Yeah, space mission, that's right, yeah. But then we had Pathfinder, so yeah.
James here has a question.
Yeah, it's based on that comment for, so I'm wondering, HM Cancri is not really a good example because we don't know the distance. But if we know, like for some of Kevin's systems, the inclination perfectly, the distance almost perfectly,
No.
and we know the signal to noise in the future for the gifting ones. Say we know all these parameters like to the T. Can we not say that, okay, we'll expect this to have the exact signal to noise, and if it's like 200 or 200.1, there's hardly any difference between these two values. I'm not sure if this is feasible at all, but can we model the space density of contaminants to say that it's not going to be relevant in our tests?
You need some chirp mass in there as well to get you your amplitude.
Oh, okay, so
Well, we have
add that to the
if you
list.
know-
I guess.
Yeah,
Just
so if
the
you know
mass-
chirp mass and sky location and inclination and distance, you don't need Lisa anymore. There's nothing left to learn. But yes, right. If you can really pin things down, then you
So
can say whether or
it-
not the data are consistent with that. Yeah.
So you could easily point that out. You're saying you can't point it out because there'll be other contaminants, but if there's like less than 1% of other sources that are contaminating this very strong signal, that'll still be very recognizable, right?
The percentage that you put on that depends on how how the errors on all those other numbers propagate through. So inclination, chirp mass, and distance all factor into the observed amplitude.
Sure.
And so whichever one of those is the least well determined is going to be the one that sets how accurately you can look for departures from the expected amplitude and say, aha, there must be contamination. But in principle, you're right.
Okay.
And we'll know the phase in that particular case. A small bit of help.
So Valeria, your hand's up.
I think it was for James.
No,
Oh,
Or
it was
you
for
had it?
James. Okay.
no,
No.
I have a question, but only if James is satisfied with the.
Okay.
Yes, okay. Okay, so I guess it's again goes to Tyson. Just we haven't mentioned this yet, but since we're talking about let's say continuous persistent Lisa sources, will they be affected by glitches and instrument interruptions and these sort of things? Because I remember seeing one of the presentation, either figures of merit or something like that. And I think I think these sources should not be affected, or even our knowledge can, I just wanted your confirmation on that.
Yeah, my confirmation is that the only thing stopping us between now and being able to deal with arbitrary instrument artifacts and interruptions is labor. It's not an intellectually challenging problem. It's time spent solving the problem. So as long as we get enough hands on the problem, we'll be fine.
Okay.
If no one has comment regarding this, then Alexei, you have a question.
I have a question. It's a bit off topic, but I even have a comment. So I mean, I think there was a paper recently where they were reporting on glitches in Lisa Pathfinder. So there were some glitches, after all. So there will be glitches in Lisa for sure. And the question is a bit off topic, but still related. So I mean, thinking about gravitational lensing and about the sort of similarity between Lisa and Gaia. So in another sense, so if when people talk about Gaia data, so when they analyze the data, they also have to account for gravitational lensing by Jupiter and by the Sun. So I guess probably the similar effects are going to be affecting some of the LISA data, in particular, probably some sources interaction of the Sun when they're collected are going to be lensed, and interaction of Jupiter as well. So is that accounted for, and can we measure something new about the solar system this way?
I don't think the LISA measurement has enough precision to worry about those sorts of effects.
Yeah, that's going to be some dark second for sure. Yeah.
But maybe like we have to know very precisely, right? Or as precise as we can, the position of the spacecrafts, I guess. And maybe then we have to know the solar system well as well. As for the other space missions, like, does it enter there somehow?
Well, the solar system will know well. because the solar system knowledge is already well known, and the pulsar timing people are making it better because they need it even better. So we'll know that well. I think the onus is going to be on us, on knowledge of the spacecraft, right?
So there are two places where the spacecraft ephemerides enter into the problem. You need to know the light travel time between spacecraft to nauseating precision to do the interferometry.
Mm-hmm.
And so if we have analyzable data, we then by construction have the light travel time between spacecraft to exquisite precision, more precision than anyone could ever want to do with. And then the absolute locations of the spacecraft relative to the solar system barycenter tell you how the gravitational wave signal projects onto those interferometry channels. So you need to know those as well, but to less precision, then you need to know the light travel time, particularly for ultra compact binaries, which are sufficiently low frequency that they live in the long wavelength limit almost exclusively. And so the wavelength of the signal is much, much larger than the arm length of the detector. So you have plenty of slop in the absolute ranges to the spacecraft. If you care about higher frequency signals that get up into the transfer frequency where the wavelength is comparable to the arm lengths, then those absolute locations start to matter more because you're trying to use that for position reconstruction. And so people battling, low mass black hole mergers with higher harmonics are going to have much more concern about ephemerides than the folks doing ultra compact binaries. But because it all goes into a global fit, you sort of get their work for free.
Mm-hmm.
Maybe to add to that, I mean, just beyond deflection so if gravitational wave passes through the sun and comes to us, probably it's going to be magnified a little bit as well. So, I mean, is there any effect measurable that way?
I doubt it. The error bars and amplitude are big.
Mm-hmm.
Okay, I don't see any hands up. Is there anything you'd like to discuss? Is that a no? Okay, I take it as a no. But thank you, everyone, for your contribution. It's a very interesting discussion session, and I guess
Yeah.
we'll see most of you in like 10 minutes.
Yeah, so at 6 UK time, we will wrap up the meeting. So if you would like, you can join, or you can
Rest.
have a rest. Yeah. But for the recap, you should follow the link for the supermassive black hole binaries discussion.
Well, it's also listed as the wrap-up link. Is that the same link in the schedule?
Yes.
Yeah.
it is
Okay,
the same.
perfect. Okay. See y'all in a
See you
bit.
there.
Thank you.
Thank you. Bye.
I can be at the wrap up. So let me just say thank you for organizing. I really, really enjoyed this workshop, and it's so hard to have the hybrid discussions, but this time it just really, really worked well. So thank you all for organizing.
We're glad you were here, Sylvia. Thanks for participating. It's been great having you.
Valeria and her team.
Andres, Elliot, here and here. I mean, yeah, they will hopefully get credit in the 5 minutes.
Okay. See you all soon.
Bye all.
Bye.
Bye.